Hi, I'm Alex Udris, and thanks for joining us tonight for Boldmethod Pro Live. Tonight we're going to be talking about some transonic effects, specifically Mach tuck and Coffin corner. And this is kind of a follow-up to the last Boldmethod Pro Live where we started to talk about critical Mach number. But don't worry if you missed that or if you're not familiar with critical Mach number, we're going to intro by kind of getting into some of that. Tonight we've got Corey Comerick on chat, so if there's anything that I confuse you with or lose you at, or if you want me to go into more detail, throw that out into the chat. Corey will grab that and send it over to Colin Cutler, who's our technical director tonight. He'll work it into the presentation. Don't wait for the end. Keep the questions coming all the way throughout. It keeps this much more interesting. And so with that, we're actually going to jump in pretty quickly here. And we're going to start, as I said, by understanding the concept of the critical Mach number and Mach itself. So with that, we'll start with the speed of sound, and we'll look at what happens there. And then from there, we're going to talk about shockwave formation and how that can affect the aircraft's control and its pitching and possibly rolling moments. And then we're going to talk about how to recover from some of those effects. And then we're going to finish by looking at Coffin corner. So we'll start by jumping into the iPad and talking about the speed of sound. The speed of sound is essentially, there we go. Okay, there we go. The speed of sound is affected by one thing, and that's the temperature of the air. Okay, so here we've got some incredibly warm air, 50 degrees Celsius, and you can see how fast those molecules are moving around and how much they move. But as that air cools down, notice that they're moving much slower. So watch that again. So here, when the air is hot, the molecules move far and they move quickly. But as the air starts to cool down, those molecules move only a little bit and they move very, very slowly. And so, okay, what does that have to do with Mach and the speed of sound? When we think about the speed of sound, all we're really thinking about is how fast air can move pressure forward. Okay, if I was to clap my hands and you hear that clap, well, all that's happening is sound waves are rippling out from my hands. And that's happening because the molecules of air are just bumping into each other and pushing those waves further out. The faster the air molecules move, the farther they go in less time, the faster those pressure waves can travel. That is the speed of sound. And so the one thing, it's not density, it's not altitude that affects the speed of sound, it's just simply the temperature of the air. The warmer the air is, the faster the speed of sound because those air molecules are moving faster and they can transmit pressure waves faster. Okay, so with that you're going, but wait a second, I know that the speed of sound changes with altitude. And it does because air temperature changes with altitude. So if we go back to the iPad, this is today's temperature sounding in Denver. And what you can see, if you look at the ground where we start, okay, I think we're about 25 degrees Celsius when we took this. You can see that air temperature drops off quickly up to 9,000 and then a little slower, and then it continues dropping all the way up to 39,000. And had this sounding gone up into the stratosphere, you would have noticed that this would have probably started to level out and maybe even increase. Okay, so that is also showing you the change in the speed of sound. In this case, the speed of sound would be the fastest right at the surface in Denver. And as you go up, the speed of sound will start to slow down. Okay, it's going to slow down pretty quickly here up to 9,000 feet. And then it continues to slow down as we go up to 12,000, but not as fast. And then again, since the temperature drops quickly up to 18, it'll slow down quite a bit. And then it just follows that temperature curve. And if we got to the stratosphere, you might notice that the speed of sound actually starts to even out. It becomes constant. It doesn't change much. And then as we go up a little higher, you'll notice that as the temperature slowly increases, and we're talking about very, very cold temperatures, maybe like, in the negative 60s or negative 50 Celsius. So this is extremely cold, but you'll notice that the speed of sound will start to increase along with that temperature as well. So when we're talking about the speed of sound, it's easy to overcomplicate it, to talk about, well, what altitude and what speed, but just start by thinking about it as simply The warmer the air is, the more the molecules bounce around, the faster they can transmit those pressure waves. And so the speed of sound is always going to follow the temperature profile of the air. Okay, so let's talk about how that affects our airplane. We'll go back to the iPad, and if you tuned in on our last Pro, you've probably seen this, but it's a good thing to review. This right here is a basic airfoil. And in this case, we're flying at about Mach 0.5, so half of the speed of sound. What that basically means is that the airfoil is moving slower than what air could transmit pressure waves. So for example, if I was to clap, the clap would move out ahead faster than the wing would move. And so essentially, you could think about this as a car, if you, or even an airplane. You're sitting in an airport, you look at an airplane on final, you can hear the airplane because the airplane is moving slower than the speed of sound. The pressure waves from the airplane's engine, the air flowing over the wing, all of that noise is being transmitted out at the speed of sound. And as the listener, okay, I'm hearing those before the airplane actually passes me. So that's the interesting thing about the speed of sound. You can really see it or think about it just when you watch something, a car or an airplane. You can hear them because the noise is moving at the speed of sound, but they're moving much slower. Okay, let's go back to the iPad and see what happens as the airplane starts to speed up and approach the speed of sound. You'll notice that those pressure waves start to pack in together, and right at the speed of sound, boom, they basically form what you could call a bow wave. And we actually call this a shock wave, and there are several different kinds of shock waves. But what's happened here at Mach 1.0 is that the airplane, or in this case, the airfoil, is moving exactly as fast as air pressure can move. So all those pressure waves pile up right on the very front of the airfoil or the airplane's nose. And if you were to look at an actual aircraft, you'd see these pressure waves at Mach 1 all over the airfoil, the nose, on the tail, on the wings. And the other interesting thing is if you were to watch an airplane approach at Mach 1 or faster, you wouldn't hear anything. And the reason you wouldn't hear anything is because the sound that the aircraft's emitting is moving forward at the same speed that the airplane is. So the first time that you would hear the airplane is as it passes right over you. That's because the airplane is now traveling Mach 1 or faster. Okay, looks like we've got a question.
Okay, Damon's got a good question based on that chart with the temperature soundings. And he says this: so what if the temperature is minus 60 degrees outside and I clap my hands? Is the speed of the sound that I'm making with my hands going to be a lot slower?
You were exactly right. It will. And when we talk about a lot slower, it's still very, very fast, but it will be a lot slower. Sound will transmit more slowly on a cold, frigid winter day than it will on a hot day. And if you were to be able to time it, you could actually think about this. We do notice the speed of sound when you start to think about something like lightning and thunder, because you see the lightning and then you hear the thunder, right? Well, that's the speed of sound at work, right? The light from the lightning is traveling at the speed of light, and the sound from the thunder, the pressure, really, the thunder is just the pressure expanding from the heat of the lightning. Well, that pressure expansion is happening at the speed of sound, much, much slower. So if you were to have a thunderstorm in the summer and it was let's say it's 5 miles away, you see the lightning and then you hear the thunder. Okay, now imagine you got thunder snow. It's in the winter and it's still 5 miles away. You're going to see the lightning, but it will take a lot longer for you to hear the thunder because the speed of sound is so much slower. And that's kind of a way to think about it. And when we think about a shock wave on an airplane, that really is just airflow moving at the speed of sound. So if you go back and you look at the iPad here, essentially at Mach 1, what you end up with is this big shock wave because all the pressure that's being pushed forward by this airfoil can't travel any faster than the airfoil itself. So it just piles up and angles off. Okay. That doesn't happen immediately. And if you think about an airplane, You know, the airfoil or the airflow accelerates as it starts to move over an airfoil, right? Here we could be subsonic, but then as we go up and we go over the airfoil, that air is accelerated. That's what's generating lift, so it becomes faster. And at some point, if we're close enough to Mach 1, that airflow could become supersonic. Now, in this case, we've drawn it on an airfoil. It could be the wing, it could be the tail, but it doesn't necessarily need to be an airfoil. It could be the fuselage itself. But at some point in time, as you approach Mach 1 in an airplane, somewhere along that airframe, the airflow will start to accelerate to supersonic speeds. That's what we call the critical Mach number. The critical Mach number is the speed at which, at some place on your airplane, you start to get some supersonic flow. You're starting to generate supersonic air movement. And again, it could just be just a tiny area on the wing or on the top of the fuselage or in the wing root, but that speed will happen slower than Mach 1. So on old airplanes, it could happen maybe Mach 0.85. With new designs, we've been able to get a lot of airplanes to the point where they can get very, very close to Mach 1 before they start to accelerate air into supersonic speeds. But it will always happen at a speed earlier than Mach 1. So when you talk about a critical Mach number, that's always going to be a number slower than Mach 1. Okay, so let's go back to this picture and take a look at this, because this is what we call a normal shockwave. And there are different kinds of shockwaves. We'll do a video on that one day. But the interesting thing about a normal shockwave is if you look at the airflow, as the airflow passes through the shockwave, it does not change direction. But just about everything else with that airflow does start to change. And let's talk about that. Air is able to accelerate to supersonic speeds very easily. It's completely smooth. There's no turbulence. It accelerates just fine. And the problem becomes where it starts to slow down to subsonic speeds. As soon as the airflow starts to slow down below Mach 1, it generates this big pressure wave. And that's because all the pressure is essentially backing up. It can no longer move as fast as the airfoil is moving. That pressure wave causes a lot of problems. It loses a ton of energy. Okay, so basically we're going to go in the supersonic area. It's moving extremely fast. So we're going to go from very low pressure to back. In fact, I'll do that in blue so it makes more sense. That's not blue. Okay, we're going to do that in very low pressure over here. And then as soon as we cross that shock wave, the air gets to high pressure. And that change happens almost instantaneously. And because of that, it bleeds all of the energy out of the air. Maybe not all, but a lot of it. Okay, if you think about a stall, what happens in a stall? Well, the pressure gradient along the wing is adverse. You're moving from low pressure, and as you get towards the trailing edge of the root, the wing, you're going to move towards higher pressure. That's what we call an adverse pressure gradient. You're going from low to high. Air naturally wants to go from high to low, okay? But if it goes from low to high, it's taking energy out of the air. And eventually, it takes so much energy out of the air that it no longer stays attached to the wing. And it starts to separate, and that separation can cause a loss of lift. And as that separation grows up the back of the wing, that could start to cause our total amount of lift to decrease. And when the total amount of lift decreases, we've entered a stall. Okay, so essentially, when we start taking energy away from the air, when it's moving across an adverse pressure gradient and it's losing that energy, it can separate from the wing and it can cause a stall. Okay, so now we look at a shock wave. And the problem here is this is like 1,000 times worse than what you would normally get off of just a normal pressure gradient, because the change is so aggressive as it crosses the shock wave. It's so drastic that it can quickly cause airflow to separate. And so, boom, all of the airflow here now separates off. Okay, so if we think about a normal wing, I've got a slide here. Typically, this is a basic airfoil. And if we think about what's normally happening on a wing, the air comes up, it goes over, and then it washes down. Okay, and then you've got some air that goes over the bottom as well. And if you think about what's going to happen here, it speeds up, right? We're getting faster and faster and faster, and we reach this point of maximum low pressure right here. Okay, so after it crosses maybe this point, now it starts to slow down and it gets back to, I'm going to put an N here for normal pressure. Okay, it's essentially getting itself back to normal pressure. We start at normal pressure and then we move towards low pressure and then we move back towards normal pressure again. Okay, when you think about that, what that means is we get this lifting shape on the wing and it looks something like this. I'm going to clear this and draw that again so you can kind of see it. The entire wing is generating lift. You'll notice most of the lift shows up right here. And that point is about 25% of Mach. Mach means mean aerodynamic chord, the average chord of your airfoil. And when we talk about chord, we'll go back and take a look at that. When we talk about chord, chord is the distance from the leading edge to the trailing edge. That's what chord is. It's basically, you just measure from the tip to the tip, and you would measure your entire airfoil and then average those distances out, and then you end up with Mach, or mean aerodynamic chord. And in subsonic flight, this point right here, what you can call the center of lift or the center of pressure, that's going to happen right about 25% of mean aerodynamic chord. The problem is when we start to add a shockwave. So let's go back to our shockwave slide. Everything gets messed up. Okay, we used to have this lifting force which looked kind of maybe like this and trailed off. Well, all that's gone now because you're not generating lift generally behind that shockwave. So now all of a sudden the airplane loses a massive amount of lift. Okay, it can only generate lift basically right here. And that lift distribution is fairly even. So as opposed to the center of pressure being maybe right here, it might start to move back to right here. But the big problem is we can quickly start to lose lift. Okay, we're going to get into this in depth in just a second, but it looks like we've got another question. And I'm going to carefully drink water here as Colin brings up that question.
As I hit the wrong button. Okay, we got a question from Damon again here. And actually, there's a follow-up question from James. Damon's question is this. Is the sonic wave related to the sonic boom that you would hear from an airplane? And to follow that up, I'm just going to say James is here.
Yeah.
What he wants to know is the point where you hear the sonic boom the moment where you exceed the speed of sound?
That is a great question. If you're in the airplane, you'll never hear the sonic boom. That's the first thing. You'll just ride along with the airplane. They don't hear the boom, but the people on the ground will. So let's take a look at this again. This is a massive airplane, but let's just imagine what's happening. That's how that bow wave works. And actually there's a trailing wave here. And you end up with these kind of reverse N waves that kind of go underneath there. And we'll talk about that in detail on another day. But if you're this person standing right there, okay, that's you.
That's a nice drawing, by the way.
That's why I'm not the graphic artist. Okay, so that's you. And you're sitting there on the ground, okay? You're going to hear this sonic boom when that wave passes over you. Okay, essentially, boom. When those waves pass over you, that's when you're going to hear the sonic boom. And that's what you're really you're hearing is the bow wave, or the not even the bow wave, but the pressure waves on the airplane. That's what's reaching you. And you may actually see the airplane pass overhead before the sonic boom reaches you. And that's because those sonic boom waves are trailing out. Okay, so think about this. If you're in the airplane, you would constantly, if those waves were crossing you, you would just constantly hear the pressure change, and you don't. You won't even notice it. So the airplane crosses the sound barrier, you don't get a boom. And it's not, people think the sonic boom is a one-time thing. As I punch through the barrier, I get a boom. Nope, the sonic boom is a continuous thing. Essentially is just a wave right over the ground, and everybody on the ground, as that wave passes over them, they hear the boom, and the boom is just constantly moving. That's what a sonic boom is. So, you know, if you were able to move faster than the airplane and to jump back in front of the wave and back in front of the wave, you'd hear the boom each time. So the boom is really just a continuous pressure wave. It doesn't happen once, it happens the entire time that aircraft's exceeding the speed of sound. Okay, looks like we got another question.
Okay, next question has to do with the shockwave over the top of the wing, and that is, how does the pressure past the shockwave change instantly, or how does it change so quickly? Or why does it change so quickly?
Essentially, that's a good question, and I'm going to try to explain it the best I can without doing more research. But essentially, what's happening is those pressure waves are backing up. Once you get subsonic, the airflow is moving. The airflow pressure waves can no longer move forward. Let me do this. Let me do a little more research on that, because there's also oblique shock waves, expansion waves, am I missing anything? Normal, oblique, expansion. I think that's it.
I think you got it.
I think I got all of them. Let me do this. I'm going to answer that in more detail on a video on pressure waves, because I want to do a little more research before I jump in too much as to why that's piling up that way. Otherwise, I might give you something that's overly simplified and not really right. Okay, let's go back and talk a little bit about what's happening with this shockwave again. We've talked about the fact that once you generate the shockwave, even though the airplane is not going supersonic, as soon as that shockwave shows up, we can start to run into problems because we can generate separation. We also talked about the fact that as soon as the shockwave shows up, lift that at one point in time might be centered here, can start to move backwards possibly on the wing. The interesting thing, I'm going to go back to the slides. The interesting thing is if you look at a subsonic wing, that's not 25%. That's more like 25%. That would be your subsonic lift. But our supersonic lift is essentially at 50%. So subsonic lift is 25. 25% Mach, and supersonic lift moves back to 50% Mach. Okay, if we think about this, this causes a big trim change, right? And that's because the center of gravity and the center of pressure or the center of lift work together to create some torque, a pitching moment down. And what counters that? Well, it's our tail. Our tail down force is what counters that. And so if that center of pressure starts to move suddenly, now all of a sudden the aircraft's going to start to pitch. We're going to need completely different control pressures. We're going to need completely different trim. And if that change happens rapidly or nearly instantaneously, it can be very, very difficult to control. Okay, so let's talk about that. As we start to see the shock wave form on the airplane, we're not always exactly sure where it will form first. First of all, it depends on the aircraft's design. It also depends on our maneuvering or whether we have any control surfaces deflected. All of these things can change where supersonic flow starts to happen first. But when it does happen, it can very quickly change how the aircraft starts to fly. And a lot of people have heard of the term Mach tuck. Mach tuck is where an airplane flying level starts to enter what we call the transonic range. It may not be to Mach 1 yet, or it might be just above. So the transonic range is where you start to see supersonic flow in the airplane, maybe 0.8 or 0.85. It depends on each airplane and the flight conditions. And then kind of ends once full supersonic flow has been established. So just slightly above Mach 1. So as we get into that transonic range, aircraft can experience what's called Mach tuck, where they suddenly pitch over. And if you think about that, that causes a real problem. Because if we didn't want to go faster than Mach 1, if we ended up too fast and got into this transonic regime by mistake and exceeded the critical Mach number by mistake, we don't want to go any faster. And Mach tuck, on the other hand, now that pitches us down, next thing you know, you're going a lot faster. So we'll talk about why that happens now, and we'll look at some different conditions on the airplane. And the key thing with this is each of these conditions could happen. Some airplanes will experience all or some, and you could experience different conditions depending on whether you're maneuvering, whether you're banking. So really, you don't always know what to expect as the aircraft enters a transonic range if it was never meant to do so. If you're flying an airplane that was meant to fly through the transonic range, completely different design. But if you're flying something like an Embraer 145 or a Phenom or a 737, these airplanes were not meant to fly through that range. You're never exactly sure what's going to happen. Okay, so the first thing that we're going to take a look at is what happens if we end up at with a shock wave at the root of the aircraft first. Okay, so essentially by the root of the aircraft, I mean you might start to form a little shock wave maybe right here. Okay, that would be at the root. Okay, and let's just say this is happening symmetrically. It's happening on both wings at the same time. So we've got this little area of supersonic flow. And by little, I mean right here in front of it, this is sped up to maybe supersonic. Okay, everything else on the airplane is subsonic. But now we have separation happening coming off right here. Well, first of all, this is going to change the aircraft's center of lift. And if you think about it, the root generates it's got a lot of surface area. It generates a lot of lift. Okay, but now we've cut away a significant part of that. So we've taken away a lot of the lift contribution from the aircraft's wing root. And if you look at the swept back wing, look where it is. It's all behind the aircraft's wing root, right? So in this scenario, okay, even discounting the fact that shock waves can move the center of pressure a little aft, in this scenario, you would find that the center of pressure on an airplane might move from here back to there. You could see that essentially, I'm going to draw that with a smaller arrow. The center of pressure is moving back. Okay, so what does that mean? Well, let's take a look at this 737. You know Boldmethod's made it when we have our own custom painted 737. Okay, so let's start with that tail down or take a look at just the basic concept of CG here, right? You have the center of gravity forward of the center of pressure, also known as the center of lift. That wants to pitch the nose down. We're balancing that with a tail down force. We have an upside down wing essentially on our horizontal stabilizer. That's keeping the nose up. If this lift suddenly starts to jump back, we have a different arm between the center of gravity and the center of pressure. Now let's look at those. So that's, if we look at the original arm, fairly short, the new arm, longer. Okay, so basic leverage, right? With basic leverage, as we increase the length of the arm, you end up with more torque, right? And the problem with changing the center of pressure and its interaction with the center of gravity is that there is a lot of force at the center of gravity, okay? So very little changes in arm can cause some pretty big problems. That's why when you look at especially a light aircraft, you have fairly narrow CG envelopes, maybe 1.5 feet, 2 feet. You know, transport category aircraft, their CG envelope is still very narrow. Okay, that's why you ever see every once in a while they have to move passengers around to keep aircraft in the CG envelope. So if your center of pressure was to jump back several feet, you could end up with a massive change in nose down pitching moment. It would aggressively start to pitch down, okay? And the problem that you start to run into is not necessarily that your tail can't generate enough tail down force to keep the nose up. It's that by trying to use your elevator to solve the problem, you could quickly create supersonic flow over the elevator and completely remove the elevator's effectiveness, and you essentially can't stop that nose from pitching down. Okay, so let's take a look at the elevator and kind of see what's going on here. Remember, I said the elevator is an upside down wing, right? It's a wing that's meant to generate lift going down. That's what it does, okay? So you've got the relative wind. We'll draw the relative wind right here, kind of coming through, okay? That's our relative wind. And if we want to generate a little bit of lift, more lift going down, what would we do? Well, we would deflect that elevator. I'm going to draw that a little further back. We deflect that up. And the reason we do that is because that essentially creates, you can kind of see it at the very end of the video, a positive angle of attack, right? And that positive angle of attack would increase the magnitude of our lift. Okay, so by pulling back on my yoke in my 737, okay, what am I doing? I'm increasing the tail down force. I'm increasing the tail down lift on my elevator. Okay, so as I increase that lift, I'm increasing camber, I'm getting a bigger pressure difference between low and high. You know, when we think about a wing, low's on top, high's in the bottom, but when we think about a stabilizer, a horizontal stabilizer, the low is on the bottom and the high is on the top. And as I continue to pull back, I'm accelerating the air more and more, and eventually I could form a shockwave on that horizontal stabilizer. Okay, so let's go back and you can see what happens. As soon as that shockwave forms, not only may I lose surface area to generate lift, so I don't have the ability to generate nearly as much lift or tail down force off the elevator, but the other problem is look what happens with separation. The airflow separates behind that shockwave, and look where our elevator is. When I'm possibly moving my yoke, the only part on the tail that on light aircraft and some other aircraft that would move is the elevator itself. And now the elevator is behind separated air. So one of the problems you run into with a conventional horizontal stabilizer with an elevator on the back is if you start to experience Mach tuck, what's going to happen is as you bring that yoke back to try to solve the problem, you'll end up with supersonic flow on the bottom of your horizontal stabilizer. Not only does that decrease the amount of tail down force you can generate because you have a smaller lifting area, but it's blanketing your elevator, the only thing that you can move, and it's preventing you now from changing the aircraft's angle of attack. So essentially, your tail just became fairly useless. And this is why when you look at aircraft that are meant to operate close to transonic speeds or supersonically, you'll notice that they use stabilators or all flyable horizontal stabilizers. As opposed to an elevator section in the back, the entire thing pivots in the airflow. That way you don't lose your control effectiveness as you enter transonic and supersonic speed ranges. Now you still may see some tabs back there, and people go, well, isn't there a really small elevator back there? Those are usually trim tabs or control tabs. But on most transonic or supersonic aircraft, that elevator would no longer be effective. And so instead, we use all flyable stabilators. And you might see them on like a Piper Cherokee. It's not because the airplane's meant to go supersonic. It's just because that's the way the designers decided to do it for aerodynamic reasons. Okay, so what happens? You end up with this wing root shockwave first, which moves your center of pressure aft. Now you got a bigger arm between the center of pressure and the center of gravity. The nose starts to tuck down, and you can't pull back on the yoke because if you do and you try, you end up stalling out the tail, and now the nose just keeps going down. Your airspeed keeps going faster. How do you get the airplane out of this? Obviously, bring the thrust levers back. But that might not be enough. The airplane's going really, really fast. So what can you do to slow the jet down before things start to come off the side of it? Well, we can deploy our spoilers. We could possibly deploy our flaps, and we could deploy our landing gear. People go, well, wait a second. If you're above critical Mach, putting your landing gear down, you're going to have some serious problems. you will lose the landing gear doors, most likely, but the landing gear themselves will probably remain welded down. They're incredibly strong. In fact, you probably will be able to land on them no problem. So inadvertent Mach tuck, essentially, you're going to start putting drag devices out there into the airflow to try to generate enough drag to get the airplane to slow down. In an airplane that was not meant to fly in the transonic regime, oftentimes if you experience Mach tuck, the only way to get the nose back up is not to try to use your control surfaces, but to try to slow the airplane down using your drag devices. Once you slow it down below the point where you have supersonic flow, you can regain control surface effectiveness and start to fly the airplane out. Okay, there's a less known version of this, and you could really think of this as Mach pitch up. As opposed to tucking down, you could end up in a case where the aircraft starts to pitch up. Okay, so let's take a look at that. I'm going to pull up that slide. What would happen if we ended up with the Shockwave at the tip of the wing first? Maybe an aileron, a little aileron deployed there and accelerated the airflow. Something happened, and all of a sudden we have this little Shockwave that forms out here on the tips. Okay? Well, what's going to happen is the center of pressure is going to start to move again. And what might have been the center of pressure here will start to, sorry, I'm just changing the ink, will start to move up here. It's going to move essentially forward. So what does that mean when we look at the airplane? Well, our old arm between the center of gravity and the center of pressure is going to get smaller. And so now, essentially, you end up with too much tail down force, and the aircraft's nose is going to start to pitch up on you. This is less known, it's less talked about, but if your wingtips were to stall first, this is something that you can end up with. Okay, there's another reason that the airplane could start to tuck down. And if you take a look at this loss of downwash on tail, let's think about what normally happens as air flows over the airplane, okay? Normally, you have your relative wind that comes up, crosses the wing, and then it flows down smoothly. And that smooth airflow flows over your horizontal stabilizer, allowing it to generate lift as a tail down force. But in this scenario, if we have a shock wave that's formed on the wing, okay, let's say there's a shock wave that's formed right here. Now we've created all of this turbulent airflow coming back, and that can blanket your horizontal stabilizer. So now, as opposed to having the ability to generate a lot of tail down force, it may not be able to generate tail down force at all. And even if the center of pressure has not changed location, you've lost essentially that right there, and so the aircraft starts to pitch nose down. So even if the center of pressure doesn't move around on the wing because of a wing root stall first, if the separation behind the shock wave starts to blanket the horizontal stabilizer, now you lose the ability to generate tail down force, and the airplane wants to tuck under as well. Okay, next question.
Okay, next up, Bama Pilot wants to know, do these swept wings help reduce the shock waves?
Okay, great question. So let's take a look at the swept wing. Let's see. We're going to zoom in on this one here and pull it over. That should work. So what we've done on a swept wing is essentially we've changed the direction of the airfoil. So if you were to look at a non-swept wing, and I'm just going to kind of draw one out quickly. If you just looked at your rectangular Piper wing, looks something like that, okay, an old Cherokee. And we want to look at the camber lines.
Oh, we can't see what you just drew, Alex.
Look at that. Can you see
zoom
it?
out a little bit more? There you go.
You see it now?
Yep. You are good now.
Okay, perfect. Okay, so if we look at the camber lines here, they're going to go like this. And if you think about where that relative wind is coming from, it's coming just like this. Okay, it's coming essentially parallel to those camber lines. Okay, so now let's take a look at what we've done to the camber lines on our swept wing. So you can see the swept wing there. or the chord, I'm calling them camber lines, and I should be calling them chord lines. It's my fault. Chord lines. If we look at these chord lines here, they've been turned at an angle. Okay, so the chord lines have been turned at an angle, but if we look at the relative wind is still coming straight. It's still coming basically right down the airplane. So essentially, your aircraft's chord is no longer aligned with the relative wind. So let's go through and just take a look at one of those. So here's a chord line here. Here's your relative wind. I'm going to draw that a little smaller. Something like that. Now, essentially what we do is we break that chord into two components, or the wind into two components. So let's do that with the wind. We end up with one component of wind that is flowing parallel and one that is perpendicular. Okay, so, sorry, just like that. And so if you look at these, okay, so here is your parallel component of relative wind, and here is your perpendicular component of relative wind. We call this right here chordwise flow. So if I draw that out, you'll see chordwise flow and spanwise flow. And the chordwise flow, because we've broken the relative wind into two different components. If you think back to a triangle, right? A squared plus B squared equals C squared. Well, C squared is always going to be bigger than A and B. So as we start to break the relative wind into components, okay, the chordwise and the spanwise components, those components are always smaller than the total relative wind. So by sweeping essentially the wing back, what we're doing is we're effectively slowing down the wind over the wing, because the chord or the camber of the wing only accelerates the component of air that is flying parallel to the chord line. And so essentially, because that's now smaller, by sweeping the wing back, the air gets accelerated less and less and less. So as you add more and more sweep back, essentially the wing starts to feel like it is flying slower and slower and slower, because the relative wind is essentially less and less direct. There's two problems with this. One of the problems is that the wing feels like it's flying much slower. So when we're flying close to a critical Mach number, that's fantastic. When we're taking off or landing, we run into some bigger problems. Essentially, swept wings have very bad low-speed characteristics. So you need to add slats on the front, maybe expensive or big Fowler flaps on the back. Not only are those systems expensive, but they're heavy and they're complicated and they require more maintenance. But that's what you need to do, because a swept wing airplane has poor slow speed performance. It really feels like it's going slow. So it's going to have a much higher stall speed if that wing was clean. The other problem that you run into, if you take a look at this again, is all of that spanwise flow starts to pile up. You would think that it's kind of innocuous, but it isn't. What it ends up doing is it thickens the boundary layer right here. Essentially, it removes energy from the air at the tips of the wings. Normally, we design aircraft so that they stall at the root of the wing first. But when you end up with a lot of spanwise flow, it tends to stall from the tip of the wing first. And the problem with that is that's typically where your control surfaces are, so the aircraft can be very difficult to control as it goes into a stall. So that's another downside of swept wings. Okay, let's take a look. We talked a little bit about the horizontal stabilizer, and let's take a look at some things that we can do to try to preserve elevator effectiveness as we start to get towards that critical Mach number. Because if you think about it, as you start to get fast, if you need to apply back pressure and you have a conventional elevator on the back of the airplane, as you start to apply more and more back pressure, you're going to speed up the airflow underneath that horizontal stabilizer, and you could develop a shock wave. That shock wave could cause separation, and that separation would then render your elevator useless. So let's take a look at this L-39 Albatross, which is a subsonic airplane. But what you can see here are all of these vortex generators. So vortex generators are just angled pieces of metal, but what they do is they generate a little vortex that swirls and pumps high energy air into the boundary layer. And so those vortex generators are essentially going to keep the airflow energized and attached to the bottom of the horizontal stabilizer. And so if the horizontal stabilizer starts to get close to supersonic flow, the VGs will both delay the shockwave, they delay the critical Mach number on the horizontal stabilizer, and if a small shockwave forms, they can help pump air into the boundary layer to keep it attached or minimize the amount of separation. So this is unique because typically we see VGs on the top of a wing, and again, they're there to pump in energy on the top of the wing where the airflow is accelerating and then going through the adverse pressure gradient. And you can see those on a wing to prevent shockwave formation or delay separation. You could see them to decrease stall speed because again, anytime you're pumping air into or pumping energy into the air, you're going to delay separation, so they'll decrease stall speed. But if you see them on the bottom of a horizontal stabilizer and you see an elevator behind it, there's a good chance they're there to prevent separation due to critical Mach number or supersonic flow. Okay, there's one other thing to think about, and if you look at this 737, you can see that it's rolling, and that is asymmetrical shock. Okay, so we're rolling here to the left. And the reason we're doing that is in this case, we've generated a shock wave. I'm going to draw a little smaller line on this wing, but there is no shock wave matching on the opposite wing. And so that's going to cause a loss of lift here on the left wing, and the airplane's going to want to roll towards the left. So why could this happen? Well, one of the cases could be maybe this, most aircraft are configured now with spoilers. And spoilers essentially create drag to drop a wing or get rid of lift is the right way to look at it, to drop a wing, as opposed to accelerating air to raise a wing. A spoiler is just going to kill lift, allowing the wing to drop, as opposed to traditional ailerons, which generate lift on the rising wing, speeding up the air and causing it to raise. But if you were using ailerons at a speed close to your critical Mach number, and you tried to lift a wing with an aileron, that would accelerate the flow over the aileron and could cause that flow to go supersonic and the wing would drop. So we call this control reversal. And on conventionally aileron-rigged airplanes, that's a problem as they enter the transonic range. You try to roll and the airplane ends up going the opposite direction. Again, we don't want to accelerate airflow over the wing when we're getting close to our critical Mach number. So one of the ways we essentially protect an aircraft from this is we use spoilers on aircraft that operate close to their critical Mach numbers. Spoilers, as I said, they basically kill lift. They pop up, they can add drag, they get rid of lift, and they cause the wing to drop. So they're not accelerating airflow the same way. They could accelerate it a little bit, but essentially they're forcing the wing down as opposed to trying to raise the wing. And if you look at an airliner, oftentimes you'll see both ailerons and spoilers, but you'll notice when you're flying a cruise flight, those ailerons aren't moving, they're locked into position. It's just the spoilers that are controlling the aircraft's roll. Okay, let's take this into Coffin Corner. What I've drawn here on the iPad is an example of two important lines, our stall speed right here, and then essentially our maximum Mach number, or you could look at this as the point where we start to experience supersonic flow. Okay, Mach buffet. Remember, the speed of sound gets slower as we climb higher. Okay, so this line makes sense. Okay, and at sea level, it's fast, and it slows down as we get higher up. Stall speed is going to increase as we get higher up. Okay, so essentially the air is less dense. We need to fly the aircraft faster to prevent it from stalling. At some point, the stall speed and the overspeed will end up meeting. And this point right here, we call Coffin Corner. Okay, so essentially what we call it Coffin Corner because if the aircraft if the aircraft's flying at a speed right here, okay, and it starts to get too slow, okay, you have very little room to decelerate before you end up hitting your slow speed stall. But you also have very little room to speed up before you were to overspeed or experience Mach buffet. So essentially, you may be flying in a window where you only have a few knots either side of your current cruise speed, And if you slow down more than a couple knots, the aircraft stalls. If you speed up more than a couple knots, you end up with supersonic flow and the aircraft experiences a Mach buffet. In the past, older aircraft essentially were capable of flying faster than their critical Mach number. And so this green line here you could look at as the aircraft's maximum speed. Okay, so at sea level, the airplane doesn't generate enough thrust to get faster than the speed of sound. Okay, but at some point in time, it does have enough thrust on it to get faster, maybe not in the speed of sound, but faster than its overspeed number, its critical Mach number. So at some point at cruise altitude, there's still enough thrust left on older aircraft to get past their maximum Mach number, possibly in level flight. Those airplanes are capable of flying in Coffin corner. They've got enough power at high altitudes where they could exceed, again, not necessarily the speed of sound, but they could get critical Mach, they could get supersonic flow somewhere on the airplane. And that typically would only happen in high altitude cruise. But now if you look at a modern airplane, they're pretty much what we call thrust limited. Okay, so as opposed to this green line, we end up with the blue line. So first of all, you notice that the aircraft's power is essentially flat here until we reach a certain altitude. That's because most aircraft's engines now are derated or flat rated. And when we say derated or flat rated, essentially the jet's capable of producing a lot more power, but the FADEC system limits the amount of power that the jet can produce. And there can be a couple reasons. It could be aircraft and airframe limits. It could be controllability limits. It could be pressure limits inside the engine. There could be a lot of things. But typically, every new modern jet engine that you see is in some way derated. It's going to limit the amount of thrust that it can produce at low altitudes. But as we start to climb up, it can continue to push in a little bit more fuel and a little bit more fuel and a little bit more fuel. It can maintain that thrust rating because essentially, even though the air is getting less dense, it doesn't know it. It's still got headroom left to go. Eventually, that engine is going to run out of headroom. And just like a basic jet engine, it's going to start to lose power with altitude too. So if you look at a more modern aircraft, you'll notice essentially its thrust capability is flat, and then it also starts to fall off. But you'll notice here that oftentimes it can only generate enough thrust to get close to overspeed, but in level flight, many airplanes have a difficult time actually getting to overspeed or critical Mach. And that's because essentially economy is more important right now than speed. Engines are much more efficient, they consume less fuel, and because of that, they don't necessarily have the ability to push enough thrust to get us in level flight all the way up to our critical Mach number. Okay, looks like we got a question.
Okay, and I'm going to hop in here. I don't have a graphic up, but just a good point someone asked about old airplanes versus new airplanes. Maybe could you give us maybe an example of it, like what is considered an older airplane that might have this critical Mach buffet problem, and maybe a new one that might be thrust limited?
Sure. So when we talk about old, I'm talking about a DC-8, 707, 727. These aircraft and their traditional engines could easily get into Coffin corner. But when you start to talk about new aircraft, 175s, in fact, the CRJ series, the Embraer 145s, they don't have enough thrust on board in cruise flight typically to get themselves into a critical Mach scenario in level flight. Descending flight, absolutely. But in level flight, these airplanes typically can't get there. Same thing would be true, I think, and I can't say for sure, but I would bet with something like a 787, the modern 737s. Again, all of these airplanes are designed for efficiency as opposed to essentially when fuel was very cheap and they're looking for speed. And so many of these aircraft, again, you could still experience critical Mach if you were diving. If you're descending, you've got the ability to generate a lot more speed. But in level flight, modern aircraft are typically thrust limited. One of the problems that we run up with thrust limited aircraft is they can end up essentially at a cruising speed that may not be very close to Mach buffet, but can be very, very close to their stalling speed. So if we go back to this chart, you could end up in a scenario possibly where the airplane was flying, let's say, maybe right here, okay? It wasn't using full power yet. It was flying right there. And one of the things to think about is the jet engine's power output depends on a lot of factors, temperature, density of the air. But one easy thing that you can take a look at is the air becomes less dense. The jet engine either needs to spin it faster, essentially, to try to get the same amount of compression, and eventually you run out of the ability to do that. So as you get to some point, as the air becomes less and less dense, the jet engine starts to lose power. Well, as the air becomes warmer, it gets less dense. And I know that at altitude, it's really cold, like 50 below. But the change from -60 to -50 still changes the air's density. And it will still reduce the power output of a jet engine. So if we go back to this drawing, what can happen there is as that temperature starts to warm, you'll notice right here, the speed we're flying, that's our maximum thrust setting. And so as the air continues to warm, if we maintain altitude at this temperature right here, the airplane would have actually started to decelerate and would now be at our stall speed. And so this can be very insidious. You may not even notice it happening. You're flying along in cruise, okay? And the air starts to warm up. And again, it's not getting really hot. It goes from maybe -60 to -45. But the reality is your jet engine's power output starts to decrease. And eventually your airplane starts to slow down. And then eventually it can hit its stall point. And that is essentially what we call kind of a hot and high scenario in a jet, different than density altitude hot and high in a prop. It's the fact that that air starts to warm up and then all of a sudden you lose engine power. And I shouldn't say all of a sudden, it's happening gradually. You just don't notice it. And then your airspeed starts creeping back, and the next thing you know, you get a low speed warning. So that's more common. When we talk about modern aircraft, we're really not talking about coffin corner the way we used to in the 80s, in the 70s, in the 60s, and the 50s, where coffin corner was a much more realistic place to fly. In modern aircraft, we're typically not there. There are some other things that we can do. One of them here I'm going to show you is a supercritical wing. So a supercritical wing changes the camber design of the wing to increase the critical Mach number. And so essentially, if you were to look at an old school wing, okay, so a traditional non-supercritical wing, a traditionally cambered wing, you could end up with a very sharp coffin corner here, where you don't have a lot of room between your overspeed and your stall. But a supercritical wing essentially spreads that out. It allows you to get much faster before you reach supersonic flow. And so now you'll notice that you have a much larger area in here. You have all of this extra area to fly. So supercritical wings not only allow you to fly faster, but they also essentially kind of eliminate some of coffin corner. Okay, looks like we got a question.
Okay, we have a lot of questions. In fact, I think I have over 15 of them. A lot of them are very technical and advanced, so I'm not going to put you on the hot seat. But what we'll try to do is, with a lot of these, we'll try to grab these and answer them when we post this to the site. But Damon has this question. His is pretty specific, but I'm going to wrap it back with maybe more of a generalization. What Damon says is this: at what point would 200 knots indicated airspeed be equivalent to Mach 1? What I'm going to say is, could you maybe walk us through how Mach number changes as you climb, and maybe what's going to happen to your indicated airspeed as you climb?
Yeah, that's a great question. So if you think about indicated airspeed, so first of all, Mach is related to true airspeed. So relating it back to indicated airspeed is going to be a little bit more complicated. And the reason is because essentially all Mach number is your true airspeed over the true airspeed of the speed of sound. So if your true airspeed is 300 knots and the speed of sound is 600 knots, you're flying Mach 0.5, okay? So when we go to look at indicated airspeed is going to drop off as the air pressure decreases. And the reason for that is because as we get, basically the pitot tube is what's sensing your indicated airspeed. And as you get higher at the same true airspeed, there's just less air up there. The air is less dense, so it creates less force on the airspeed indicator. And so because of that, as we go up, essentially your indicated airspeed is going to slow down. So if you think about, let me see here. I don't know if I've got a, let me see if I've got a, I don't have a blank slide, but we'll just draw it on the bottom of this. If you think about your true airspeed, your indicated airspeed is going to start to slow down as you go up. So let me draw the axes here. Connor, are you guys able to see that pretty well?
Yep, that's perfect right there.
Okay, so let's go into the highlighter. Let's say that our true airspeed is this magenta color. Okay, so the true airspeed is going to be constant. Your indicated airspeed, essentially at sea level on a standard day, would be about the same. And it's going to start to drop off. Okay, so the speed of sound now, let's draw that in a different color. I'll switch over to the pen and we'll draw the speed of sound as orange. The speed of sound is going to start maybe here, and it's going to go back as well. So the question on where 200 knots indicated would end up matching up with the speed of sound is going to depend on a couple factors. And those factors are going to be, number one, what's your true airspeed? So what's the air density at your altitude? What's the temperature at your altitude? There's a lot of factors. So it would be kind of hard to say that without looking at, essentially a very specific condition. One of the interesting things to think about on an older, an original style round dial airspeed indicator in a jet is that they had a barber pole. That barber pole was their maximum Mach number, essentially their maximum speed. And the flight computer would actually compute it, or the pressure system would compute it. So as they started climbing, it would figure out the speed of sound from true airspeed and then relate that back to indicated airspeed. And so you would see that speed would be very high, okay? And then it would start to swing down and get slower as you climb. And so essentially this little barber pole needle would come down. That would be your maximum Mach number. That's not the speed of sound. It's a speed slower than that, but it's representative of how close you're getting to the speed of sound. On a glass cockpit aircraft, the barber pole is now a barber section of the tape, and that tape will also start to come down. So essentially, as you get higher, at sea level, you may not see the barber pole at all, and in cruise altitude, you might see a little bit of it at the very top of your display, and then if the temperature starts to get really, really cold, you might see it come down even more. Okay, next question.
Okay, we got time for one last question, and like I said, we'll try to answer all the other ones when we post this to the site, or as many as we can. But Jimmy wants to know this. What procedure would a pilot use if they got themselves in a coffin corner situation?
The key thing there is to descend. You really want to maintain your airspeed, but to get the aircraft out of coffin corner, the best solution is to descend. Because let's go back to that coffin corner slide. And I'm just going to rewind this all the way to the beginning. We'll zoom in a little bit. Okay, essentially, if you're flying right here and you realize, wow, I've got very little room to speed up or slow down, I'm kind of on the verge of a stall, and I'm on the verge of overspeed, all you can really do to fix that is to get this dot lower. Ask ATC for a lower altitude. And there's a couple reasons that you could end up in coffin corner. Again, the air density could change or the air temperature can change. And so, you may be flying well below your coffin corner, and then all of a sudden that air density starts to change and you find that you're much higher in that coffin corner shape than you thought. And your solution is to get down. Again, airspeed control. Don't let the airspeed speed up or slow down, and then, get clearance and descend out of that. Take the airplane to a lower flight level. Okay, that's all the time we've got for tonight. There are a couple things. Oshkosh starts in 2 weeks, a little under 2 weeks. We'll be speaking Monday, Tuesday, and Wednesday at the EAA Pilot Proficiency Center. Each of those seminars start at 12:45, about an hour long. The Pilot Proficiency Center is, I don't know if it's air conditioned, but it is cooled. Is it air conditioned?
It is air conditioned.
It's air conditioned.
One of the best places to be on a hot day.
There you go. We're the last group right before the air show. So if you want to watch the air show Monday, Tuesday, or Wednesday, before the show, stop out, watch our presentations. The schedule is online at EAA. We'll post it at Boldmethod as well. As I said, they're entirely free. And the EAA Pilot Proficiency Center is kind of that main square in the Boeing Plaza. It's an easy place to find. We hope we see you there. Otherwise, we're going to be walking around Oshkosh all week. So if you see us, we'd love to say hi. Stop by and grab us. Other than that, we will not be doing a live show the week of Oshkosh. We'll let you know our updated schedule here shortly. And with tonight's show, if you like this, please give us a thumbs up on YouTube. It definitely helps our search rank. And let us know in the comments or through email to info or support@boldmethod.com. Let us know what you'd like to hear about next. Thanks again for tuning in tonight. Have a great night.